Welcome to our topic on percent yield. This is our final topic for the unit on limiting reactants and stoichiometry. This is the last thing to tie in to the stoichiometric part of this unit. With percent yield, what we're looking at as a chemist is a yield means to form or produce from chemical reactions. So when we're talking yield, we're talking about how much of the product did we make. In an ideal situation, you want 100% yield. That means everything you are putting in as reactants are coming out as products. But however, we find that oftentimes as chemists, we don't have 100% yield. There are many different variables that can go into why or why not our yield is 100% or not 100%. Some of it could be as simple as human error. For example, maybe you didn't heat something up long enough or stir it well enough. Or if you're filtering, which we'll see in the lab on Wednesday, maybe you were left some of your product in the original beaker and didn't collect it in the filter paper. So there's lots of places where human error, or maybe there's even error with your lab equipment in terms of a scale is reading inaccurately, whatever it may be, that your percent yield is less than 100. A lot of times we look at yield, especially through manufacturing viewpoint, and your goal as a manufacturer is you're trying to turn a profit. You don't want to have a waste of chemical, and you want to get as much bang for your buck and have 100% yield or as close to it as possible. And so you don't want to have a waste of money, and you want to look for and make sure that you're maintaining a percent yield that your company is in support of. So when we look at a chemical reaction, there are two things we're going to look for. Theoretical yield, and this is how much, according to pencil and paper, aka a mass to mass conversion, is needed and what will be formed. So we're going to see mass to mass again. And then we have the actual yield. The only way you get actual yield is through the data you collect while back in the lab. And so we have a formula that works with percent yield. Percent yield is equal to the actual yield, so what you actually formed in the lab, over your theoretical yield. This is how much you should make according to the mass to mass conversion. This, I use the AT acronym to just kind of remember that it's actual over theoretical. So I remember this as the AT equation. And it's just a goofy way, but it works to remember the formula here. Another trick is your percent yield can never be over 100%. There's no way to feasibly make more than what you are allowed. So you can't have 110% yield. Otherwise, you're breaking the law of conservation of mass, and that's not feasible with chemical reactions. So your percent yield should be 100%, meaning you got everything right, so to speak, or less. Okay, the lower you get to zero, the worse you are performing. Okay. This first reaction really is kind of an easy one of just plugging into the equation. So I'm not going to balance the equation. We won't need it for this one, but for the upcoming ones we will, and I'll explain why we need it in the upcoming ones. In the problem, they state right away that we have a theoretical yield of 25 grams, and they're talking about the yield of water because that's the product. That is what is yielding, forming, or being produced. They tell us here that the actual yield is 20 grams. Okay, so this problem directly gives you both the actual and the theoretical. Most of the time, that's not the case. So percent yield is the actual yield over the theoretical yield, where the actual yield was 20 grams. And if everything was done correctly in the lab, theoretically, if things went perfectly, you should have formed 25 grams. And I realized I just flip-flopped my colors. I was using pink for theoretical, but you guys get the idea. And then we're multiplying this by 100. If you're not sure on what fraction, aka decimal, 20 is over 25, we just take 20, divide by 25, multiply that out by 100, and that's one thing some of you guys are forgetting with percentages, and 80% of our product is formed. Again, you are achieving or striving for 100% yield. And so you could look at what are you doing in this situation to improve and bring that number up from 80. Here, this is more of what you see stereotypically with a percent yield situation. So chlorobenzene is this product here, because again, yield is always going to be solving for percent of a product. And this chlorobenzene is used in aspirin. There is a second product here, hydrochloric acid. We don't care about that. as a manufacturer company, this is a byproduct. You would find a way to dispose of it or use it in some other application. And they formed it by taking benzene and reacting it with chlorine gas. So starting out, we have carbon with 6, hydrogen with 6. It's split amongst 2 products here, and there is 6. And we have 2 chlorine because it's split up. So I'm going to go ahead and just write in ones here just to show that we did look at it and balance it in case we lose track of things. Okay. Here, it's asking what is the theoretical yield if 45.6 grams of benzene reacts. So what we're looking at is, according to the mass-to-mass conversion, if we put this much of this reactant through, how much of this product can we make? And so this is where it becomes a mass-to-mass. So we're going to go ahead and start with 45.6 grams of benzene, which benzene, they tell us up here, is the C6H6. Okay? So when we go through a mass-to-mass, the first step is to convert grams to moles through the use of molar mass. So I have 1 mole as my numerator here. And my denominator, if I'm not sure, I have 6 hydrogen and 6 times 12.01 for my carbon. And I have 78.06 grams for my denominator here. All right. Where I'm now at is I want to figure out how much benzene of this chlorobenzene can I get from my starting amount of benzene. So I'm still going to show it. So I show that units are canceling because, again, my grams have canceled here. I'm going to use my mole ratio, where 1 mole of benzene is my denominator and 1 mole of chlorobenzene is my numerator. I'm going to then have one last step in my mass to mass in that I need the molar mass of this chlorobenzene. 6 times 12.01 plus 5 hydrogen plus, that's 5, and then 35.45 for my chlorine, for a mass of 112.51 grams, and that's in 1 mole of this substance. Okay. So keeping track, I'm now at grams, and specifically grams of my chlorobenzene. So what this tells me once I get my answer is if I use all 45.6 grams and everything goes according to plan in the lab, this is how much should result according to the mathematical side of things. So we go ahead and divide by our molar mass here. Don't need to do anything with the ratio because it's just a 1-to-1 ratio. And then I'm going to go ahead and multiply by my mass of 112.51. So I have 3 significant figures. I'm going to keep 3 significant figures, and I get 65.7 grams of the chlorobenzene. So in most situations, we have to do this mass to mass, and again, this is then my theoretical value. It then wants to know what is the percent yield, where it's the actual yield over the theoretical yield. We calculated the theoretical yield up here. So we should have formed 65.7 grams. Okay. In a percent yield problem, they have to give you the actual yield, and they do that right here. So our actual yield is 63.7 grams. The only way to get an actual yield is it has to be given to you, or you're performing the lab where you can go and then measure that. So again, when we see our lab, your actual yield is going to be based on the results that you actually obtained back in the lab. So we take 63.7, divide it out by 65.7, and times by 100 to percent it. Okay. So it looks like with rounding, I'm going to go ahead and say that it was 97.0% yield of the chlorobenzene. So that means there was about 3% of our benzene was not properly used in forming the product, the outcome that we wanted. Okay. So one last example then, we have the formation of carbon dioxide and sulfur dioxide through the combustion of carbon disulfide with oxygen. So here we have, it's wanting to know what's the percent of sulfur dioxide. So this is the product that we are looking for. If you start with 25 grams of this carbon disulfide and it produces 45. So let's start by balancing. Carbon looks good. My sulfur are not balanced. If I place a coefficient 2 here, that takes care of the sulfur. And in total, I have 2 times 2, so 4 oxygen, plus another 2 for a grand total of 6 on the product side. So I'm going to go ahead and use a 3 here to then balance out the oxygen. So for percent yield, we know percent yield is the actual yield over the theoretical yield. And we're looking for the percent yield specifically of the sulfur dioxide, the SO2. That helps me digest and break down what I should be using for actual and what I should be using for theoretical. It says right here produces 45 grams of sulfur dioxide. So that is what we are forming. Percent yield will always be what we use for a product. So this is the amount of product we made, and this is, again, going to be my actual yield. What we are finding is if we burned all of this carbon disulfide, how many grams of sulfur dioxide should it have produced without any human or experimental error? So what we have is a mass to mass where we're going from 25 grams of my reactant, CS2, and we're going to change it to grams of the product, and specifically they want to know the yield of the sulfur dioxide. So the first step is to go through moles, and that's with the use of molar mass. We know carbon is 12.01. Sulfur should be, 32.07? Or 32.07. And we've got 2 of them because of the subscript. So our molar mass is going to be 76.15. And that allows grams of carbon disulfide to cancel. I need to then get a mole ratio. My coefficient here is 1 mole of CS2 is to 2 moles of my sulfur dioxide. I need this in grams, so I need the molar mass here. So we have 32.07 for my sulfur, and then 32 because I have 2 oxygens. So that's 64.07 grams, and that's in 1 mole of SO2. Again, the goal of this here is to solve for the theoretical. So then it's a number crunching game of 25 divided by 76.15. I then multiply by my mole ratio of 2 to 1, so I just got to times by 2, times 64.07. So hypothetically, this should have formed 42.07 grams. And actually, I'm going to go ahead and say 42.1 to keep appropriate number of sig figs. So my denominator here, again, should be greater or equal to my actual yield. So 42.1 grams is my denominator, and we just got to multiply by 100. So by taking 40.5 divided by 42.1 times by 100, we get 96.2% yield. Okay. So again, the thing that gets tricky is which do you use for your actual and what do you use for your theoretical. For your theoretical, you always put the mass of the reactant, so CS2 was a reactant, and you convert it through to grams of your product. In this case, the product being the SO2. The actual yield always has to be provided to you in the problem.